welcome you all again. Now I am inviting Professor Biplab Basak from IIT Delhi. He will speak on a note on three-dimensional normal pseudomanifold. We are grateful to Professor Biplab for accepting our invitation in very short notice. Professor Biplab.
Yeah, thank you.
Yeah.
So shall I share my screen?
Yeah, you can.
Yeah, so am I audible properly?
Yeah, you are.
Okay. Talk. So I shall talk on a note on three-dimensional normal pseudomanifolds. So let's start with the basic outline of this talk. So first I start with basic definitions. So most of the definitions are well known for the topologist, but I will recall them for the beginners. And then I talk about the motivation, that is the platform behind this research area. And then I state some main results related to our work. And then we show the outline of the proofs. So basically I shall remove the technical parts of the proof and I will give the outline only. And then I shall show some recent progress and future directions. So first start with the that basic definition. So what is a D-simplex? So a D-simplex is a D-dimensional polytope which is the convex hull of its D plus 1 points. So that's mean a zero simplex is just a vertex and one simplex is just a line segment, a two simplex is a triangle, a three simplex is a tetrahedron and so on. Now, if I take a finite collection of simplices in some Rn, then that collection is called a simplicial complex if it satisfies the following two properties. So first of all, if I take any simplex from K, then any phase of that simplex must be in K. So that is the first property. And the second property is if we take any two simplices in K, then they are either disjoint or their intersection is a common phase of both of the simplices. Now, if I take union of those simplices in some Rn, then it will be a compact polyhedron. And if we take that subspace topology of that Rn, okay, then it will be a topological space, and that topological space is called the geometric carrier of the simplicial complex K. And if that topological space is a manifold M, we say that K is a triangulation of that manifold M. So here is one example. Let K be the collection of these simplices. So that's mean here we have six zero simplices, namely the vertex A, B, C, D, E, F. So we have 15 edges. These are the 15 edges, and we have 10 triangles. Okay, so here you can see in this figure as well, right? So that's mean this collection, if you can easily check that this collection satisfies all of these two properties. So therefore, this collection is a simplicial complex. And this is the geometric carrier of K. Okay, so to visualize this as a compact polyhedron, you need at least dimension 4, and you can check that this is nothing but RP2. So therefore, we can say that this K is a triangulation of this topological space, which is RP2. Fine. Now we define join. So join of a two simplices. Now, if we take one I simplex sigma and one j simplex tau, then their join, that is sigma join tau, is a I plus j plus 1 dimensional simplex. Okay, and this is this one only. So that's mean we take all possible points from sigma and tau and make their convex combinations. Okay, so that's mean if we take two zero simplices, that's mean two vertices, then their join will be a line segment, right? And you can check the dimension 0 plus 1, that is a one simplex. Now similarly, if we take join of one simplex and a point, that is a vertex, then their join will be a triangle. Now if we take two two say edges, then we can think about them as a skew lines kind of thing, and then we can make that convex combination. Then we will get a three simplex. So again, that's formula that 1 plus 1 plus 1. Okay, so this is the join of any two simplices. One can define that. Now in terms of join, one can define that link and star of any simplex. So let K be your simplicial complex, and we want to find the link of an I simplex sigma. Then link of sigma will be all of the collection of simplices in K, that is beta. Those are disjoint from sigma, but their join with sigma is in K. Okay, so let's see this in a example. So look at this example. So this is my simplicial complex K, right? Geometric carrier of the simplicial complex K. Now, if I take this sigma as this vertex A, this one, okay, then if you can check that the red colored edges, if you take any red colored edges, say BC, then BC join with A is this yellow colored triangle, and this is in K, right? So therefore, this edge is in the link of A. And similarly, you can see that all of the red colored edges are in the link of A. So therefore, link of A is a simplicial complex, which is nothing but this red colored pentagon. So this way we defined a simplicial link of any simplex. Okay, and this is also a simplicial complex. Now similarly, we can define that star of a simplex. So first we suppose we want to find the star of an I simplex sigma. Then what we will do? We first take that link of sigma, and we take any element of that link of sigma, okay, and then join with sigma, okay, and then we take all possible faces of that. And this collection is also a simplicial complex, and it is called the star of the simplex sigma. For an example, here in this example, if I want to find the star of the vertex A, then we know this red colored pentagon is the link, and we joined with each of the face, each of the line with A, and then we get these yellow colored triangles. Then we take all possible faces of those triangles. Then this collections, okay, will be a will be the star of the simplex A. Okay, and this is the geometric area. So you can see it is just a two ball, right? That yellow colored region. Now there is another concept called F vector. So for a d-dimensional simplicial complex K, its F vector is this one, that is starting from F0 up to Fd, where F0 is the number of I dimensional faces of K. So that's mean F0 is the number of vertices, F1 is the number of edges, and similarly we can define F2, F3 and Fd, that is the number of the D simplices. So here you can check that in this example for this K, F0 will be 6 because the number of vertices is 6, F1 is 15 because number of edges is 15, and F2 is 10 because number of triangles is 10, right? So 5 yellow colored triangle and 5 this pink colored triangle. Yeah, so any question? Okay. So now in terms of this f vector, we can define the g vector as well. But in this talk, we specially focused on only one term of the g vector, that is g2. Okay. And g2 defined by this formula, that is f1 minus d plus 1 f0 plus d plus 2 choose 2. Okay. Now from this you can check that. So whenever we have a triangulation of a manifold, then that f0 and f1 varies. So therefore this g2 is not an invariant, right? Even uh, for a particular manifold, we may have two different triangulations, say k1 and k2, which has different g2, right? But if we restrict ourselves into dimension 2, then this one can be expressed in terms of Euler characteristic. So that's mean if I take any triangulation of a closed surface S, then this G2 of that triangulation will be this one, and which can be just compute by this Euler characteristic, which is just this one. Okay, so therefore this G2 is topological invariant in dimension 2. And you can check by this formula that G2 of sphere will be 0. That's mean G2 of a triangulation of G2 of right of sphere will be 0. And if we take any triangulation of RP2, then G2 of that triangulation will be 3. And similarly, G2 of torus and Klein bottle will be 6. So therefore, you can say that for any closed connected surface K, G2 of K is just 3B1K, where B1 is the first Betti number of K with Z2 coefficients. Fine. Now, a three-dimensional simplicial complex K is called a three-dimensional normal pseudomanifold if link of every vertex is a triangulation of a closed surface. Okay, so it can be sphere, it can be RP2, or it can be any uh, connected sum of these RP2 or torus, right? Now, if link of every vertex is a triangulation of a sphere, then the normal pseudo manifold is actually a manifold. So therefore, we can say that a manifold is just a normal pseudo manifolds with no singular vertices. And we here we use two terms. One is singular vertex and one is non-singular vertex. So if link of a vertex is sphere, then we call it is a non-singular vertex. Okay. And if link of a vertex is not a sphere, that is, it is just RP2 or torus or some connected topics of connected sum of those, then we say that vertex is a singular vertex, and that surface is called the singularity of that vertex. So therefore, normal pseudo manifold with no singular vertices is manifold actually. Now there are some results which we can take from this 1970s. So first of all, Kalai proved that so for any normal three pseudomanifold K, G2 of K is bigger or equal to G2 of link of any vertices. So for a three pseudomanifold K, we know that link of V is a closed connected surface, right? So therefore, and we have already seen that that term is always bigger or equal to 0, right? Because it is a multiple of 3. We have seen that. That is a 3 times B1 of that surface, right? So therefore, from this we can say that G2 of K is always bigger or equal to K. Now, from a work of work up from 1970, it is clear that when K represents a 3 manifold, okay, and G2 of K is less or equal to 9, then K is a triangulation of a 3 sphere. Note that. So when we deal with only three manifolds, not the normal pseudo manifolds. Okay, so if we take normal pseudo manifolds, then this classification will be little bit difficult because there will be many singular vertices there. But if we stick ourselves only on a three manifold, then G2 of K is less or equal to 9 will imply K is a triangulation of a three sphere. Moreover, in this work, he gave that combinatorial characterization of those spheres. That's to mean he proved that if G2 of K is 0 and K is a three manifold, then K is a stacked sphere. And if G2 of K less than equal to 9, then K will be obtained from a boundary of a four simplex by some combinatorial operations. Okay, so what is a stacked sphere? So stacked sphere is a triangulation of a D sphere formed by, so we start with a boundary of a D plus one simplex and then subdividing facets. So in other words, you can take some number of D plus one simplices and stack them together through a D face. Okay, then the resulting complex will be a D plus one ball. Now, if you take the boundary of that D plus one ball, that will be a stacked D sphere. So you will see this in terms of examples. Suppose you have these four tetrahedron, okay, and you stack them together with this color. So you stack them together and this will be this, okay. So from this you will get this. Now this resulting complex is a three ball, right? Now if you take the boundary of this three ball, so that is a triangulation of a two sphere, right? So that triangulation of a two sphere is called a stacked two sphere. And similarly, you can define stacked D sphere. Okay. Now for a normal three pseudomanifold K, the complete combinatorial description of K for G2 less than equal to 2 are known due to them. So we have already seen that Kalai proved that if G2 equal to 0, okay, so then it is a stacked sphere. And in 2011, Nebo and Novinsky proved that if G2 equal to 1 and K is a normal three pseudomanifold, then it is a polytopic sphere. So that's when it is a three sphere topologically, but it has a special type or special proprietary commutatorial property. So for an example, this will be a polytopic sphere and it will come from a boundary of a uh, four simplex by some commutatorial operations. And then Zheng proved this and he proved that again. So if G2 equal to 2 and K is a uh, normal three pseudomanifold, then this K will be obtained from a boundary of a uh, four simplex by some commutatorial operations. Okay. Now, uh, so now if you take G2 equal to 3, then in general topology, in general dimension, it is very difficult to construct because we will not have any restriction, okay, or we do not have any control on the singularities. So we restricted ourselves into dimension 3, and in this one we give the topological and commutatorial description of K when G2 is 3. Okay, we proved that if K is a normal three pseudomanifold with G2 of K is 3, then its topological object is either sphere or suspension of RP2. So we also give that combinatorial characterization as well. So we will see later. So first of all, we discuss what is suspension of RP2. So this is actually very well known for the topologist, but yeah, I define for the beginners. So what is a suspension of RP2? So first you take a copies of RP2 and then a product with closed interval say 0, 1. Then the resulting complex will be a manifold with boundary. Okay, so it will have two boundary components and both boundary components are RP2 only. Then you will just cone up the boundary component separately. Now you will get a geometric carrier of a normal pseudo manifolds. Okay, so this will not be a three manifold because link of this vertex and this vertex are not spheres. So link of these vertex are RP2. So therefore we have singularities. So this is a geometric carrier of normal pseudo manifolds, and this is called suspension of RP2. So here is our main result. So let K be a normal three pseudo manifold with at most two singularities. So let W1 and W2 be the possible singular vertices. And we have these properties. Say B1 of link of W2 is greater or equal to B1 of link of W1, and which is bigger or equal to B1 of link of any vertices. Okay. So we suppose we have these conditions. Now it is known that for a three manifold with boundary, B1 of the boundary is always even. That is very easy to prove. And this will imply that B1 of link of W2 plus B1 of link of W1 is always even. Now, since their sum is even, their difference is also even. Now, we call it as 2m. Okay, so that's mean here m depends on this number of singularities and the proper type of singularities. So now we prove that if K is a normal three pseudo manifold and G2 of K is equal to G2 of link of W2, where this satisfies this condition. So we call it is G2, we call it is as K is a normal three pseudo manifold with relatively minimal G2. Okay. So if K satisfies this condition, then we characterize K in terms of combinatorial, also topological. So topologically, this complex, that is the topological space geometric carrier of K, is homeomorphic to the topological space M. So we start with some start with this link of W1 and we product with 0 1. Okay, and then we add m number of one handles in one side. So how this m comes? So from this is my m. Okay, so we add m number of handles in one side and then we cone up the boundary components. So this is the topological characterization. So we first come to that one. So what is it? What it is in terms of figure? So suppose you have a normal three pseudo manifold which satisfies this property. Okay, and say one singularity is RP2 and another singularity is connected sum of three copies of RP2. So therefore in our case this m is 1. Okay, because b1 is 3 and sorry, b1 of link of w2 is 3 and b1 of link of w1 is 1. Okay, so therefore this is 2, so therefore m is 1. And then we prove that if g2 of k equal to 9, okay, then G2 of K will be topologically this complex. So K will be topologically this complex. So we start with RP2, okay, product with closed interval 0, 1. Okay, so we have this one. So this is a manifold with boundary with two boundary components. Now we add m number of handles one side. So since our m is 1, we add only one handle. Sorry, one number of one handle. Okay, so that's when we get this one. So this is actually RP2 and this boundary component now will be RP2 connected some with torus, or you can say by that classification surface it is just a three copies of RP2, that is connected sum of three copies of RP2, and then we cone up the boundary component this. So we prove this one. That's mean if K is a normal three pseudo manifold with G2 of K is 9, okay, and it has exactly two singularities which satisfies that relatively minimal G2, then topologically K will be this one. Now we come to the combinatorial characterization part. So combinatorially, now K will be isomorphic to the normal three pseudomanifold this. So we start with a one vertex suspension of the triangulation of link of W1, okay, and then we apply m number of vertex folding with respect to one suspension vertex, okay. So now this one vertex suspension thing is well known for those who works in this commutatorial topology. So here I want to recall this one for you. So suppose this is a triangulation of a manifold. So you can see this is a triangulation of RP2, and you want to do a one vertex suspension of this. Okay, and suppose you want to do the one vertex suspension with respect to the vertex 6. Then what you will do? You first delete 6 and all possible faces passing through 6. That's when you will have this, right? Now you add one edge through this one so that link of that edge will be that cycle. Okay, so that's mean we are going from 2 dimension to 3 dimension. Okay, here link of vertex was this pentagon. Now my link of that edge will be this pentagon. Okay, and then we make the cone over this pink region through that vertices, say 6 and 7. So we will have a 3 dimensional complex. So we introduce the new edge 6 7, that is blue colored edge, and that red colored pentagon is now the link of this one, this edge, and then we make cone over this pink color region by the vertex 6 and 7. Okay, now this is a normal 3 pseudo manifold, and you can check that link of 7 will be this previous complex, this one only, and link of 6 will be the isomorphic to this one, just replaced by that 6 will be replaced by 7. That's it. Okay, so link of 6 and link of 7, they are RP2, and link of any other vertex is just sphere. So this is a 3 dimensional normal pseudo manifold, and which is the one vertex suspension of this with respect to the vertex 6. Okay, so this is the called one vertex suspension, and then now I introduce that vertex folding. Note that combinatorially the complex was we start with a one vertex suspension of the triangulation of this, then we apply m times vertex folding. Okay, so I defined what is one vertex suspension. Now I define what is your vertex folding. So suppose we want to do a vertex folding with respect to a vertex x, then what we'll do? We first remove x, okay, and all the faces passing through x. Then the resulting complex will be a pseudo manifold with boundary, and that boundary will be the same as link of x. Now we choose two triangles in the boundary, and then we identify them. Okay, so we have to be careful about that. After the identification, we should have again normal pseudo manifolds. So therefore we define such a map. So if we can do this, right, then that boundary will be changed, and then we count off the boundary by the x again. Now this is called the vertex folding at x. So we show it in terms of picture, then it will be clear to you, because this concept is not well known in the literature. So we define this one. So suppose you have a solid torus and with a boundary coned off by this vertex, right? Now this is a pseudo manifold, right? And link of this vertex is this torus, and this is a 3 dimensional pseudo manifold. Now if we want to do vertex folding with respect to this vertex, now what we will do? We first delete this vertex. Then we will have this.
Now we choose two triangles which are of sufficient distance, right? So that's mean the distance between this vertex and this vertex is at least 3. And then we identify them. That's mean topologically what we are doing, we just pull them up and stack together. We just pull them up and then stack together, and then we actually get a solid that double torus. Okay, and then we cone off the boundary component. Now this complex, this is again a pseudo triangulation, right? Or you can say the pseudo manifold. And this pseudo manifold is a one vertex suspension of this at vertex. Okay, so this is the topological objects, and this way we do the vertex folding. Okay, so now we go to the outline of these proofs. So first of all, I recall what we have already observed that from the work of Kalai. If delta is a normal Thiev pseudomanifold, okay, then for any vertex V, G2 of delta is greater or equal to G2 of link of V. That was known. Okay. And also it was known from the Kalai's work that if this delta is relatively minimal, so that's mean if there is a vertex W2 such that G2 of delta is same as G2 of link of W2, then it must satisfy these two properties. So first property is all the singular vertices must be in link star of W2. And if there is a vertex outside of link star of W2, so this is non-singular, it is known from Y1, but he says something more. He proved that in that case, that link of V should be a stacked sphere. Okay, so that is very useful. That is very useful for this one. And we also proved this one. So we skip the proof in these slides because the proof is very technical, but that is very useful result. So it says that if delta is a three-dimensional normal pseudomanifold and say A, B, C, D be a missing facet in delta. Missing facets mean this tetrahedra is not in delta, but all of these faces, that's mean all the triangles, say ABC, BCD, ACD, and BCD, all the triangles, four triangles are in delta. Okay, so suppose this ABCD is a missing tetrahedron in delta, such that B, C, D are the non-singular vertices. That's mean link of B, link of C, and link of D are just sphere, and link of A is not separated by this arc. Okay, now observe that if ABCD is a missing tetrahedron is delta, then that BCD triangle is not in link of A, but the boundary of this one is in link of A. And here the condition is if link of A is not separated by this arc, then delta is obtained from some delta dash by a vertex folding at A. So what do we mean by not separated? So we mean this one. So say link of B, link of C, and link of D, they are sphere. Okay. Now link of A can be anything. Now here we say that link of A is not separated. So that's why link of A cannot be this. But link of A can be this one. Okay. And that link, that arc, this BCD, boundary of a triangle BCD, can be the generator of that Mobius strip, the boundary of the Mobius strip, which is embedded in that RP2, right? Then it will not separate into two parts. But we proved that that will not be the case. So if B, C, D are non-singular, then link of A, that R in the link of A cannot be in that form. Okay, so the only possibility is this and this. And we prove that if the link of if that this arc is in this form, that's mean this triangle, right, which does not separate link of A, right? Then delta is obtained from delta 1, delta dash by a vertex folding. So you will see this one. Now we move to the right. Another result, this one, link of that is lemma 4. Now it says that let delta be a three-dimensional normal pseudomanifold with two singular vertices, say W1 and W2, and such that G2 of delta is G2 of link of W2. Okay. Then there must have one delta dash such that delta is obtained from delta dash by stacking, and all the vertices and edges of delta dash are in this. Now the proof of this is very simple. Actually, we use the result by Kalai. So if V is not in star of W2, okay, then by this Kalai's result, this is a stack sphere, right? So that is a stack sphere. So that's mean it is a boundary of a stacked ball. Now we claim that that stacked ball B must have a one missing facets in delta. Why? If all the tetrahedra of B is in delta, then delta will be a complete complex. Say B union delta B star V. Okay, and that is a contradiction. So therefore, it must have a missing facets. Okay, and by our this lemma, we prove that vertex folding is not possible. So therefore, we must have this connected sum. Now, if delta is will be then delta 1 connected sum delta 2, and all of the singular vertices should lie in one part. So therefore, G2 of the other part will be 0, and again by the Kalai's result that will be stack sphere. So therefore, we can say that delta is obtained from delta 1 by stacking. Now, if we repeat this process again and again, then after some stage there will be no vertices outside of star of W2. So all the vertices should be in star of W2, and therefore, and since the G2 of delta is same as G2 of link of W2, so therefore all the edges should be in star of W2. Okay. So therefore, from now onwards, whenever we have G2 of delta is same as G2 of link of W2, then without loss, we can assume that delta satisfies this property, because otherwise delta will be obtained from this kind of pseudomanifold by only stacking. So, okay, anyway, so this might be confusing for the first time reading. So I will show you in terms of picture. Suppose this is my normal 3 pseudomanifold. Okay. So link of this vertex is torus, that is one copy of torus only, and link of this vertex is the double torus, and link of these vertices are the say stack spheres. Okay. Then if link of delta if G2 of delta is 6, that's mean if G2 of delta is same as G2 of link of this vertex, then by the Kalai's result, all the singular vertex should be in the star of this complex. So therefore, this vertex should be somewhere here. Okay, by the Kalai's result. So it should be this. And then we prove that if we have some vertices outside of this, which is stack sphere, we can remove them by unstacking. So therefore, we get by our result, we get this one. So therefore, we have this situation. Now we apply our previous lemma, which is vertex unfolding. Now in this case, we actually can do vertex unfolding, and we will have a suspension of vertices. So we state this one. So this is our main result. So let delta be a normal 3 pseudomanifold with these following properties: that delta has exactly two singular vertices, W1 and W2, and say link of W1 is some SH and link of W2 is some HG, where their difference is 2n. Okay, and say G2 of delta is G2 of link of W2, because we can assume that. Then delta is obtained from one vertex suspension of this by vertex folding. That is n number of vertex folding. Okay, so that was our main results. And right, so as I told you, so I will skip the proof. So that is the main idea actually. So we first have this, by Calais result we have this, and then we can remove those vertices this, and then we can, by the previous lemma, so this lemma, this one, we can do the vertex unfolding, and after some stage we will get the same number of singularities, the same type of singularities, and then we are able to prove that they are just suspension of that surface. So now, as a corollary, we can classify all normal 3 pseudomanifold in terms of when G2 of that normal pseudomanifold is 3. Because if G2 of delta is 3, then we first prove that delta will have at most 2 singularities. And since delta may have only these RP2 types of singularities, so therefore we will not have exactly one singularity. So there will be no singularity, that is the sphere, and by the walk-up result that will be sphere, or it has exactly 2 RP2 singularities. So therefore we can use our this result, and here n will be 0. So that will be the just one vertex suspension of RP2, and that is our result. So these are all about the main results. Now we have some recent progress and also future direction in that direction only. So we proved that if delta has G2 minimal, if delta is G2 minimal normal 3 pseudomanifold, and delta contains either 3 singular vertices including 1 RP2 or 4 singular vertices including 2 RP2, then in one of our recent work with my student, we proved that delta is obtained from a one vertex suspension of a surface and some boundary complex of 4 simplices by applying some commutative operations such as connected sum, vertex folding, and edge folding. Okay, so we proved this one, and but it remains open to give commutative calculation of delta when delta has more than 2 singularities, or right, more than 2 singularities which is other than RP2 singularity. So these are not known. Okay, so this is one open direction, and another one is this one. So we proved that, which we just present, we proved that if G2 of delta equal to G2 of link of T, and delta has exactly 2 singularity, then delta is obtained from a triangulation of a 3 sphere by a sequence of vertex folding and edge folding. Okay, so I did not define edge folding, but it is similar type of vertex folding. Now this leads to a natural question: what will be the maximum value of n such that G2 of delta less than equal to this number will imply delta will be the same manifold? And in one of our article with my student, we are able to prove that n is 9. But here we, in case of 2 singularities, we took 1 singularity as RP2. So therefore it is still open if you have 2 singular vertices or more arbitrary singularities. Okay, and to classify that to classify delta, well, that delta has relatively minimal G2, or you can find some kind of n such that G2 of delta is less or equal to that number, will imply the same type of normal pseudomanifolds. So that was the another direction, and this is the other one. So from the walk-up's result, it is known that if delta is a 3 manifold with G2 less than equal to 9, then it is a 3 sphere, but it obtained from some boundary of 4 simplicity by some sequence of operations. Okay. And in this article, we actually extend that one for that normal 3 pseudomanifold and for G2 equal to 3. And we prove that in that case, it will be coming from a boundary of 4 simplicity by the sequence of operations like X expansion, H folding, and topologically this is suspension of R2. Now in another work with my students, we again extend it for G2 equal to 4, and we prove that we will get the same type of combinatorial pseudomanifolds. Now again, it is still open for G2 from 5 onwards. So that's mean it is not known what will be the combinatorial characterization of delta when G2 of delta is 5 or 6. Okay. So these are the open possible open problems in that directions. Okay. So these are all. So these are the references. These are some recent works with my students. And thank you.
Any question? Or any comment? Okay, if there is no question, then again, I want to thank Professor Biplab for his nice talk. Thank you.
Okay, yeah,
Professor
thank you
Biplab.
all for attending, and also I apologize for that interruption at the beginning. So I have to switch to the another device.
Yeah. Okay. So thank you all of you.